Let's go back to the example of our 32-bit system with 4 kilobyte pages. Okay, and we'll use 3 segments. As before, we'll use a code segment, a heap segment, and a stack segment. So now our virtual address will look like this. It'll have this structure. Since we have 4 kilobyte pages, we'll need 12 bits. 2 to the 12 is 4096. And then we said we only need 3 segments. We have to set aside 2 bits for that, and that'll give us 4 possible segments, out of which we only use 3. So we use 12 here, 2 here, which gives us a remainder of, I guess, 18 bits for the virtual page numbers. So in addition to this, we will want to have 3 base plus bounds register pairs to store the tables, it turns out. And so only the base register will have the physical address. The bounds will just basically tell us how big the tables are. So each process will now have 3 page tables, 3 separate ones, and they are, in this case, we're going to start out with assuming that the page tables don't have to store all the possibilities, just as many as we need. Okay, so here's the scheme again, 3 segments. We have 4 possibilities, but we only use 3. That's 1 input into the page table. Then we have virtual page numbers, which is 18 bits. That's another input into our page table scheme. And then eventually what we get out of that is the location of the page frame that we want to access with this 32-bit virtual memory. And then we index or offset into the start location of the page frame to find the exact byte that we're trying to address in this virtual memory address. Okay, so once again we have just 3 segments: code, heap, and stack. We have to set aside 2 bits for that. And then you have to have virtual page numbers within each one of those page tables to give us the address in physical memory of the frame. You add the offset to find the exact byte within that frame that we need to access. So how does that structure look? So you have 3 possibilities for page tables. 0, 0, let's say, refers to code page tables, or table, it's just one table. And then 0, 1, let's say, refers to the heap page table, and 1, 0, let's say, refers to the stack page table, and 1, 1, it's just not used. We just didn't need it. Okay, and then we have to use this page table address and find the location of the page table in physical memory. And then we'll use the virtual page number inside that table. How does that look? We would show it schematically this way. So once again, 2 bits of the segment will let us know which table we're going to use. And so based on that, we'll get the location of the start of the page table in physical memory. We add that virtual page number as an index into that table. Alright, so that's what this is showing schematically. Is you know the start address, you find the index into that page table, that's the virtual page number that tells us which entry we're going to read, and then that tells us the page frame number, which is the location in physical memory of the page frame. And then we have to add the offset into that to get the exact byte of memory. So this is just sort of just like before. We have to find out where this is. Hopefully this is something that we can store in base registers so that you don't have to go to memory to get this. Okay, but then you do have to go to memory to find the table, and then you index into that. So you have to access this memory location so that we can find this memory location. But there's a little bit of addition and things like that involved as well. So the base and bounds registers are used because remember we may not use all of a page table. There might be a lot of empty entries. So to minimize the amount of empty entries, we just use as large a table as we need. It can be really large if you look at all the different combinations. So in this case, for example, it's 2 to the 18. That's pretty large. If you use another register like bounds register and we only use as many of the entries as we need, we could potentially save a lot of space as far as storing these tables. Each one of these code, heap, and stack page table. So once again, we are we're assuming that the tables are each arbitrarily sized. They're not fixed size. And so we can save by using just a register. We can say, okay, we can say how big each one of these tables are so we can track it. We don't have to go beyond the bounds and things like that. And storing these tables will also be simplified. However, there's a big problem with this. Arbitrary size page tables leads to fragmentation again. So when we combine segmentation and paging with arbitrary size page tables, we get external fragmentation again because the page tables are going to be arbitrary sizes. And it turns out that, we want to avoid that. The better solution is to break page tables into smaller pieces and use a two-level scheme, that is a directory to organize the page tables and then use um, a whole directory to find the location of the page tables. And it turns out this is actually the better solution segmentation than segmentation paging with arbitrary page table sizes. So here is the scheme that we will be looking at. This is an overview. If you have a linear page table, you have a huge table where we only use a few of the entries. In this case, 1, 2, 3, 4, 5 of the 16 page table entries are used. If you now break this up into a multi-level page table, so let's say 2-level, you have a page directory, and we see that we only use the first page table that fits over here, and then the last one. Let's say this is for the stack and this is for the heap and code. Then these two entries are invalid. So you see the zeros here, that means they're invalid. They're not in use. And so we only have 4 entries here, and then each one of these will have, let's say, 4 entries. And so we use 4 plus 4 plus 4, 12 instead of 16. And when you use more bits for each of the addresses, bigger addresses, actually the savings can be quite large. And it turns out this is what we use in most systems. We use multi-level paging. Seems really complicated. It is, but then it turns out it saves a lot of space when we look at the larger addresses like 32 and 48 or 64-bit addresses. Okay, so once again, why are we doing all of this? To save space. That's the advantage of using multi-level paging. You only allocate the needed parts of the page table, not the entire, let's say, 4 megabytes. Instead of 4 megabytes, it's actually just a handful of pages. If you have each part the same size as a page, then we can fit that part in a page, and that's ideal. So easy to allocate page tables and page directories. We'll have not much of a penalty for TLB hits because address translation will be in 1 clock cycle. The disadvantages, as you saw in the previous diagram, is that this is a little bit more complex than this. The big disadvantage is that you're adding a level of indirection. If you have a TLB miss, then you have to have 2 memory accesses to do a single memory translation. That is a total of 3 memory accesses to access a single byte of virtual memory. So what is the 2? You have to find the location of the page directory, index into that, get the entry. So that's one memory access. That will tell you the location of the page table, and then you have to index into that using the virtual page number, part of the virtual page number, and then this tells you the location of the physical um, frame number. So 1, 2 memory accesses, and then we get the frame number, and then we access the byte that we're looking for. So that's a little bit more overhead, but we do all of that mainly for one reason: to save space. Okay. So here's a detailed two-level page table example. You can find this in chapter 20 of the online book. Take a look in pages 7 through 10.